it? Okay. Yeah, like,
It's okay. This review is such a godsend. So,
yeah.
whatever way you want to post it.
Message. I got so excited when I saw that message in the group me. I was like, yes.
Yeah, same here.
Is anybody else having trouble hearing me?
No.
No, I can hear you fine.
A little bit. I'll try and talk a little louder. Sorry. Yeah, when I was in Orgo 1 of the TAs used to have reviews for us, and I thought it was like so helpful, so I figured I would like keep it going. I'm also going to join it from my iPad so I can actually like write it up and like have legible handwriting. Did you guys finish the Alex assignment?
Yeah.
No.
Yeah.
Yeah.
No.
It only took 45 hours, but yeah.
It took so long.
When you read my report, it says 50 hours.
I think my Alex took me like 80 hours or something like crazy like that.
Yeah, I started it like as soon as he posted about it, and I just finished it like yesterday. I was like,
That's
that's
awesome. It's probably like such a relief to finish it.
It feels like a weight has been lifted, but at the same time, I'm still dreading this exam because the Respondus system is just so scary, like the way it records you and sounds. Like, I don't plan on cheating. It's just the fact that something's going to be watching me.
Yeah, I just used Respondus for the first time for my biochem class last week, and I was like so nervous, and it did flag me because I had like a piece of paper like on my table, and I was like writing out what like one of the tables was because I like answer questions in my head, and then I'll like compare the answer to like what it actually is, and it flagged me. So that was like.
Are you not allowed to have a piece of paper?
You are allowed to have a piece of paper. It was just like my head was down for so long that it was like, oh, she's cheating. I was not cheating, you guys.
Yeah, I went to office hours and asked our professor about that today.
What did he say?
And what did he say?
He basically just said like, don't look down. So I was like, but
So
like
like
when
be
we're looking
writing
at
like this.
in the periodic table. But does it like log you out if you look down too much?
It'll just
Or
like
does it
kind
just
of
look-
warn you.
Okay.
It'll be like your face is out of view or something like that. So.
Because some people told me if it happens 3 times, it like kicks you out, and I got like nervous about that.
That's what happens with honor lock. I said that in the group chat in the beginning.
Oh. Okay.
Or yeah, the honor lock thing, because my friend goes to UF and it happened to her where she like has really bad eyesight. So she was like leaning in trying to read it, and they only saw half her face because she was leaning in. And it happened a couple times, and it warned her, and it locked her out and submitted the test. That's how UF works.
I hate
That's so
story.
scary.
But did
I
he
know.
say we can have like a periodic table, or we can't have that either?
No, he said that we could have a periodic table.
You can have a periodic table, and you can have like scrap paper.
Okay.
It should be like holded ups when we're taking the test, so like they know that's what we're looking at, or
I don't know.
because like I don't know, when I look at a periodic table, I like look down.
Someone said when you're doing like when you're showing the space around you, you should like show them the paper.
Yeah, so the way that I did it for my exam, obviously I didn't need a periodic table, but like I kind of like picked up my whole computer and I like showed the sides, made sure there was like nothing on my wall, showed over there. I kind of like showed my whole space, and then I picked up my scrap piece of paper and showed both sides. So I would do the same thing with a periodic table. I wouldn't really put anything on the wall just so that when you're like staring at a wall, that would look like it's cheating, like he doesn't really know what's on there.
What if we have things around us?
Yeah,
Because
like
some of these things I don't have places to put it.
Like what things? Like a
Like
poster?
like books.
I would put it on the floor, like as far away. If it's like a Orgo book, like I put mine like all the way on the other side of the room.
Yeah.
So
I have
he
a
wouldn't even
question.
like.
When we show the room, do we have to show like 360 of the room, or is it just like the area around you? Because I was a
Just
little.
the area around you. pretty much. He's not going to be like too picky. Like even though I got flagged on my exam, it wasn't like, oh, you're definitely cheating. I guess he just like looked over that one part where I was looking down and then decided that I wasn't cheating because I wasn't. So
Okay.
so a couple of tips that I have for the exam, some like things that I would definitely go into the exam knowing are the definitions. In your homework, you have this like question that's like a bunch of vocab questions. If you guys have been doing the homework, then you'll have a question like that. From what I remember on my exam, we used to have like a question that like was literally fill in the blank exactly word by word. That's when it was in person though, so I'm not sure how it's going to be since it's online, but I would definitely still know definitions. I would know how to like when you're doing like Lewis acid like Lewis acid and base questions or Bronsted-Lowry acid and base, like know the difference between those two, and then also know like, oh, this one is a Lewis acid since it's donating whatever. I would also know how to say like, oh, this carbon is sp, sp2 or sp3, and the same thing with like hydrogen, knowing how you can say that it's like S or like 1s is usually how it'll be assessed. Know the difference between like constitutional isomers and identical compounds and then resonance structures, and know how to rank boiling point, and some other things that I would know. Those like circle confirmation questions, let me tell you what they're called.
Newman projections?
Newman projections, yeah, that's what they're called. Know how to like transfer them from like one, like if it's something like this, and it'll say like, okay, this is the front carbon. It'll usually have like an arrow pointing towards it. How to like make it into a Newman projection. We can go over a question like that after. If a question asks you like which of the molecules will exhibit hydrogen bonding, know how to do that. Again, water solubility is like pretty important. And I remember chair confirmations like were really freaked me out for the first exam, but like we can go over a question like that. I'll throw up some of the notes that I have that are pretty helpful for chair confirmations. That kind of like breaks it down, and we'll do a practice question. What else? The naming compounds like IUPAC, the IUPAC system, know how to do that. Know how to assess formal charge. And know how to compare stability. If you guys are in the group me, which most of you guys probably are, I was talking about how you guys should know pKa values. You don't have to memorize pKa values. I would definitely know a couple like water, NH3, NH4, carboxylic acid, like C, bonded to C, like the pKa values of that, just because when you're taking an exam, I think it's probably going to be like 25 questions, right? Has he said how many questions it's going to be? Yeah.
No.
I today he told me it'll like during office hours, it'll probably be 25 questions in 50 minutes.
Yeah, that's how much he had it for Orgo 2 last semester. Usually in person, he'll have it as 20. So you guys can count yourselves as lucky because there's like more questions. So if you get like 2 wrong, then you have an A still. But yeah, definitely, just because those questions do have like such a bearing, like each one is 4 points, I would know pKa values personally, just because that's the difference between like a B and a C, or like an A and a B, you know what I mean? So it's better to be over prepared is what I always like to think. Also, yeah, chair confirmations and the chair confirmation stability. Let me show you guys. Let me see a couple other things. Know how to do the what are they called? Functional groups. Those are pretty important. resonance structures, how to draw those, but I guess it wouldn't necessarily be drawing. That's also a good thing about it being online, is that you're not actually drawing anything. And that's pretty much the things that I would kind of know like for sure going into the exam. So if you guys are ready to go over some practice questions.
Yeah.
Okay, awesome. So I'm gonna minimize this. And let's say that we had a question like, sorry, I should have printed this out. Actually, I do have it printed out if you guys want me to go get it. Okay, I'm gonna be right back so I can have it, like, and I'm not like at my computer trying to zoom in. Okay, let's see.
Did he say anything noting when you saw him at the office hours for the test?
What?
Yeah, one more time, please.
I said somebody went to his office hours. I was just asking if he said anything else worth noting about the test.
Not that comes to. Oh, all I asked is why we couldn't go backwards in questions and about like the time.
Oh, we can't go back.
No, he didn't really answer why though. He just can't. I think it's for like cheating purposes, I guess. I don't know.
Do you guys know if the honor lock system tracks like your eye movement or just like your head?
We're not using honor lock for this one, but honor lock's basically what we're doing, but on steroids. You said that's what we might be using for the final though.
So what are we using for the regular exams?
Respondus and lockdown browser.
Okay.
It's like the same thing, I think.
Does that track your eyes or just your face?
Honestly, I'm not sure. Probably both, but I don't know if it's a live person with honor lock. Like honor lock's a live person. I don't know if this one is.
Gotcha.
I think it was recording when I took it yesterday.
Yeah, it's just recording for a lockdown browser.
Gotcha.
Okay, so over here, this is like kind of a question, and the wording would say like something like, consider the following molecule, rank in order of increasing acidity, and then put the least acidic first. So over here, you guys probably know already, but over here we have the carbon atom is attached to two things. So we know that it's going to be sp. We have this carbon is attached to three things. Like this is 1, 2, and 3. So then it's going to be sp2. And then over here we have the carbon is attached to 4 things. And then we have sp3. And these, something that like we can just know as our like stick in the ground to tell us what direction we're going in. Over here, if we have a triple bond, then we know that this hydrogen here is going to be a super acidic hydrogen. So then obviously moving backwards, it's going to get less acidic. So if it's asking us to rank it in order of increasing acidity, then we know that this one is going to be the most acidic. And then which one do you think is going to be second, 2 or 3?
3.
2 or 3. So I have a vote for 2 and a vote for 3. So over here, how many things is this carbon attached to?
3.
Yeah. So we have 1, 2, and 3. So then we know this is going to be sp2, and then this was a sp bonded to an hs. And then over here, technically there's another hydrogen over here. So that makes this carbon and sp3 bonded to an H with a 1s. So then this one is going to be more acidic than this one. So we're going to have 3 here and then 2. So if we're ranking in order of increasing acidity, then we have 2, 3, and 1. Does that make sense to everybody?
Yeah.
Yeah.
Okay, cool. So then let's say that we have another one that's asking us to rank in order of highest boiling point. So So let's say that we have something like this. And then over here we have a double bond, and then we have a nitrogen with an NH2 on the side, so or a carbonyl with an NH2. So over here, just as a little thing, what is this called?
An alcohol? Carboxylic acid?
Is it a carboxylic acid?
It's not carboxylic acid. Carboxylic acid would be an OH over there.
Oh, yeah.
No, that's an aldehyde.
Oh,
Aldehyde?
it's an aldehyde.
Yeah, awesome, you guys. This is an aldehyde. And something like this. Do you guys know what this is?
Carbonyl.
Ketone?
Or ketone. Oh.
A carbonyl and also a ketone. Yeah, so like more formally it would be a ketone.
I thought it can't be two at once.
Well, technically in this one, a carbonyl is the C double bonded to an O.
Mm-hmm.
And then a ketone is when it has two carbons over here, like two R groups, and then that thing like that. And then it's in the center, and then it's two sp, 3 carbons on the sides. Does that make sense?
Yeah, but I thought it can only be one functional group at a time.
Technically, the functional group is a ketone. Like a carbonyl isn't necessarily a functional group.
Okay.
It's just like how we define that C double bond O. Okay, so then over here, just as a little stepping point, do you guys know what makes something what is considered hydrogen bonding? Like what's capable of hydrogen bonding?
Is it
Hydrogen bonds with fluorine, oxygen, and nitrogen, right?
Yeah, fluorine, oxygen, and nitrogen. So I remember it as hydrogen just wants to have bone. If that helps you guys remember. So over here, just looking at it, we know that something with a high boiling point will be able to hydrogen bond. So like if something can hydrogen bond, it'll have a super high boiling point. So out of these four, which one do you think will be able to hydrogen bond?
The one on the bottom left.
The last one?
Yeah, so number 4. And that is because it has this nitrogen. So if we had another molecule like this, then it would be able to do this. So let's say that we have our other molecule similar to this, and we know that hydrogen bonding is an intermolecular force. So then it would be able to bond like this, whereas the rest of them wouldn't be able to do that, especially because this one has a double bond over here. So it's not really going to want to do hydrogen bonding just because it's already pretty content with its stability, just like that. Whereas nitrogen has this like perfect lone pair right there to bond with that hydrogen. So this one only has van der Waals and dipole. And then this one also only has van der Waals and dipole. And we know van der Waals is the weakest interaction. Van der Waals and then dipole. Whereas this one here has van der Waals, dipole, and hydrogen bonding. Is everybody good with that?
Does he also ask what would be able to bond with water? Like what would be able to hydrogen bond with water?
Yeah, so if you were to ask which of the following has the highest solubility, the answer would also be question number 4, or option number 4, just because that's the only one that would really be able to bond with water, considering what like hydrogen bonding is.
Okay.
Cool.
But if that wasn't an option, so from the 3 top ones, then would they all be able to, since they could? No, they wouldn't. Or would the option number 3 be able to hydrogen bond with water?
No, this one doesn't have hydrogen bonding, so it doesn't. Maybe if it was OH, then it would. But just looking at this question as a whole, it can. Okay. Just because this is just a hydrogen on itself. Okay. It's not really stable enough to like give off, because we know hydrogen can only form one bond. So this is the only bond that the hydrogen is going to be able to form. Does that make sense?
With questions asking about solubility, the answer will always kind of be just hydrogen bonding.
Yeah, pretty much. But if it's a solubility question, it'll most likely have multiple ones that can hydrogen bond, and you just have to look at it.
Okay.
and
Thanks.
see like based on those solubility rules.
I'm sorry, can you repeat that?
So if it's asking about solubility, it'll most likely have something like hydrogen bonded to fluorine, bonded to like whatever, like a carbon, something, I don't know. Whereas if it's, and then also have like a hydrogen bonded to an oxygen, bonded to whatever. Cool.
Can we rank these just for like extensive, like extending it?
We'll go over a question for solubility in a second, and we'll do the ranking for it. Cool?
Okay, cool.
Okay.
Just to clarify though,
yes.
For this only like applies if it has a lone pair to give, right? So like if it were NH3 there, like with, and where it had a plus formal charge and it wouldn't.
It doesn't necessarily matter about the lone pair, just because that hydrogen would be able to leave, giving it a lone pair. It just has to have the ability to hydrogen bond. Like over here, this one just doesn't have the ability because this hydrogen wouldn't be able to bond to this oxygen because it's already bonded to something. We would need something like a nitrogen, fluorine, or oxygen like that. That's
Okay,
already attached to it separately.
All right.
Does that make sense?
Yeah.
Okay, cool. So then another question he might ask is rank in order of decreasing acidity. And this is where I was talking about maybe knowing the pKa values so that you're able to answer the question like pretty easily. And then
also just use
you might
your
have
periodic table and use the trends for it.
You can use the periodic table for this one and look at the trends, but I feel like when I kind of like memorize trends, I might like forget them on the exam, so it's safer to know, like, personally I'm like a numbers person, so I like memorize pKa values better than I memorize trends, if that makes sense. So then over here we're going to compare the conjugate bases, so that's like after they lose the little, conjugate bases when they lose the hydrogen, conjugate acid. Yeah, conjugate bases after they lose the hydrogen. So then over here, this conjugate base would look like this. So the oxygen has a minus charge on it. Over here, the carboxylic acid comes its conjugate base. Over here, we have something pretty similar to that, except there's a chlorine a little bit further away from it. And then over here, this one also is losing that hydrogen. So then over here, we know that resonance, does it make it more stable or does it make it less stable?
More.
Yeah, so it makes it more stable. So then, yeah, between 1, 2, 3, and 4, we'll see that 2 and 3 have resonance structures. So then this resonance structure will look like this. It's pretty much just moving where the double bond is and where those lone pairs are. So it's pretty much like the same molecule, but it just has that resonance structure. And then over here, this one also has a resonance structure where this one will have the negative that has the oxygen on it. And then this has the chlorine. And then this is kind of where pKa values like might come in handy, but just looking at them, we can see, we definitely know that either this one or this one is going to be most acidic. And what do you guys think is going to be more acidic, 2 or 3?
3.
Yeah, 3, because we have that chlorine over there that's also going to be kind of like pulling on the electron, so then it's making this hydrogen even more able to be donated. So like if something is acidic, then it's able to donate the hydrogen, and that's how we saw that in an sp carbon bonded to a hydrogen, that hydrogen really wanted to leave because those carbons were kind of like content with each other. Whereas over here, we can see that the carbon is kind of like pulling, or sorry, the chlorine is pulling those electrons towards it, making this bond between the oxygen and the hydrogen pretty weak, right? So then over here, we know that this one is going to be the most acidic.
So
and then this one would, yeah, what's up?
That the induction or no? What you just were talking about?
I guess induction is like a really hard thing to define, to be honest. So I don't really look at it when I'm looking at questions, but I guess technically it would be induction over here, if that makes sense.
Okay. Thank you.
Because the chlorine is just like pulling on the electrons. So
real quick, sorry, is the red the conjugate base?
Yeah, that's the conjugate base.
Okay, thank you.
Yeah, no problem. And then over here, now we're looking at between 1 and 4. Which one do you think is going to be more acidic, 1 or 4?
4?
Yeah, 4 is going to be more acidic than 1. And again, that's because this chlorine is going to be pulling, I guess it wouldn't be here, it would be here. It's going to be pulling on it. And again, it's going to make it weaker, that make this bond over here pretty weak. But 2 is still stronger than 4 because it does have that resonance structure. Cool?
Mm-hmm.
So then over here, this one is going to be the third most acidic. And then this one is going to be the least acidic. The black structure is the like original structure that you would be like given in the practice question for like the ranking.
Is it an acid or a base though, or are they just the black?
I guess it would be like considered the acid.
Okay.
And then this is like after it's donated its hydrogen, making it the conjugate base. And we can see the conjugate base in red.
Got it. Okay, thank you.
Yeah, no problem. So then over here, if we were going to, so the original question is rank the following in order of decreasing acidity, putting the most acidic first. So then, so decreasing acidity. I guess I'll start writing the question at the top, like in summary. But if we were looking at pKa values for this, number 2 has a pKa value of 18, and number 3 has a pKa value of 4. I feel like that would kind of be where the like blurriness is between 2 and 3. We can see that the pKa value is pretty different, and we know that the lower the pKa, the more acidic something is. And so another little note that we can put here is that strong acids have weak conjugate bases, and then we're going to compare the bases. So then over here, the answer would be 3 is greater than, or sorry, 3 is like, I guess less than, or greater, yeah, 3 is greater than 2, is greater than 4, is greater than 1. Is that good with everybody?
Cool. I have a question about ranking acids that's like kind of not related to this. So we did the worksheet for one of the days, the lecture days for acid, and on the worksheet, we were all kind of really confused because we were given like different answers by TAs. And it was about ranking acidity between, like the only difference between the 2 acids was it like one of them had like fluorine and the other had like iodine. And we were given like different answers as to which one was stronger. And I've been kind of really confused about that because in the textbook, it said that the larger atom would be more acidic, but it kept marking me wrong on the homework for that.
Interesting. Are you talking about, I know what worksheet you're talking about because the TAs are in a group me and we were all like arguing about it, and I was like, listen up you guys, it's definitely, I don't even remember what I said it was. I'm pretty sure I said it was bromine. Which one is bigger, bromine or fluorine?
Bromine.
Yeah, I said it was bromine because it was larger. And then fluorine would kind of, it's like a smaller atom. So it's really like, I'll draw it out and it'll hopefully explain it a little bit better. So we can think of fluorine looking like this. So obviously it doesn't have this many rings. But let's just say that we have fluorine, and let's say that it has its octet. Fluorine kind of only wants 7, obviously, because it's not like a halogen, but it's like pretty close to it. So it has like one less ring than the bromine does. And it was, what was it saying, ranking bases? Like which one is more basic?
It was asking what was the stronger acid?
Okay, what was the stronger acid? So stronger acid is weaker base. I drew the conjugate base before finding resonance just because I drew the conjugate base when comparing all of them because you're supposed to compare conjugate bases. So over here, stronger acid is a weaker conjugate base. I guess that's not like super helpful here, but we can think of it as this. So over here, let's say that we have the fluorine and the bromine. So bromine is a bigger atom, and so we can see that these electrons on the outside are closer to where the nucleus is, and we know that the nucleus is what's pulling in those electrons, right? So it has like a closer connection to the electrons on the outside, whereas bromine kind of has like a weaker interaction to those electrons just because it's like further away, right? And we know that acids, when we do Lewis acids, those are the ones that accept the electrons. So I guess bromine would be like a better electron acceptor, while fluorine would be a better electron acceptor. I just know that the bigger the atom is, the stronger the acid is, if that makes sense. It's just like one of those trends, I guess, that you need to know for your exam.
Yeah, I
So
was
like,
watching a video, and it said that the trend goes like to the right and then down.
Like this.
Yeah, because that's what I understood it, but for a homework question, it marked me wrong when I said that bromine was a stronger acid than chlorine. It was saying that chlorine was stronger. And
Was
that's
that
what, like,
the,
that's where this confusion was.
was that the only thing in the question, or was it like molecules that they had a
That was the
chlorine?
only, it was HBr and HCl, like that was the only difference between the two molecules.
And they're saying HCl is a stronger acid?
Yeah, that was the homework, one of my homework questions for chapter 2.
Wait, so we don't go off of electronegativity for that? We go off the size?
I think it's like electronegativity then size. Like if they're in the same.
Yeah, what is that acronym that you guys have to know?
ARIO. I think. I don't know.
It's ARIO.
Yeah, so like what is A? What is this? Resonance, induction.
Atomic size, I think.
I don't know.
I don't remember.
What is O? Honestly, with these, I'm telling you guys, pKa values, and you don't have to know anything else. That's my best advice to you guys, is just look at the chart and memorize the pKa values, and you can answer the question in like 2 minutes, like 30 seconds. Okay, it's gonna save you a lot of time.
You should know, like the most.
Just like look at the chart. Look at the chart, and if you forget the pKa values, try and find resonance structures. Compare the conjugate bases. Like we did this question. We saw that wasn't too bad, right? This is how hard the question is probably going to be on your exam. Nothing more difficult than this. Dr. Dowdy's super nice guy. He wants to see you guys succeed, I promise.
Could you say again one more time which pK values we should know? H2O, NH3, NH4, carboxylic acid, and that's all I have.
I would know the ones that are on the PowerPoint and in the book, which are probably like the same ones. Yeah, those are the ones that I would know. If the two atoms being compared are in the same column and the larger atom is more stable, they're in the same row. Melinda, is that like your little tip for everybody on how to remember? Or is this a question? Okay, yes, so if you guys want a little tip on how to compare electronegativity and stability, then Wanda gave us a super nice, awesome tip in the comments. Thank you for that. Okay, so now let's do this question. Yeah, I could have sworn that I was asking which one is more basic. That's all I'm saying. Like the one in the sheet was asking which one is more basic. I don't want to spend too much time on this just because he probably wouldn't ask a question like this on the exam. But yeah, bromine is more basic. which like was like confusing me because you guys were asking which one is more acidic, and I like remember the answer being bromine, but I'm just gonna say bromine is more basic. That's my final answer. I'm sorry if it's incorrect. Just because we know that it's able to donate the electrons more, and that's why it was making sense to me, because it has a weaker connection. So the bromine isn't like really holding on to this pair or anything. It can like just like bond to a hydrogen over here, and it can be like super happy. Whereas like fluorine really does not want to bond to fluorine, because the fluorine is like so happy. Fluorine is the most electronegative atom. It's also like something you guys can remember. So it's really not going to want to donate any of its electrons. It's like pretty content with it, even with its negative sign on there. So I guess fluorine would be considered more acidic.
Okay, so fluorine is a stronger acid and bromine is a more basic?
Because we know that with Lewis acids and bases, we know that the acids are electron acceptors, and then bases are electron donors. So obviously in this case, we're not thinking about, if we're just like looking at the molecules themselves, there's no like hydrogen to really compare it to. So we know that we're talking about Lewis. If something is a better electron donor, then that'll make it a better base. So we see between bromine and fluorine, bromine is a better base because it's able to donate those electrons better because it's not as close to the nucleus. Make sense?
Yeah, that makes sense.
Okay, awesome. So you might have a question like this. Which of the following best describes the relationship between the two? And then the options are constitutional isomers, identical compounds, resonance structures. So I actually remember doing a practice problem and getting this one wrong. So your options are constitutional isomers, resonance structures, or identical compounds. What do you guys think?
Is there supposed to be another methyl group in the second drawing? Or does it just look like that?
My bad. Thank you for catching that.
Yeah. Are they isomers?
I think so, yeah. Constitutional isomers.
They look identical.
Yeah, they look identical to me.
There's so many, so we're getting some mixed answers between constitutional isomers and identical compounds. And I know that constitutional isomers is like a super enticing like option for us, but these are actually identical compounds. We can see that this carbon atom right here, all because we can see that the only difference here is where that chlorine is. This carbon atom right here is connected to a carbon, to, let's see how many carbons, like 1, 2, 3 carbons and 1 chlorine. Over here, this carbon atom is connected to 1, 2, 3, like 1, 2, 3 carbons and 1 chlorine. All we can see is that it kind of just like shifted up, maybe like it moved in or out of the plane, but that's still making it an identical compound. And a constitutional isomer, let's say like this is our original structure, might be something that looks like this, where we just moved the methyl and the chlorine, that switched. A resonance structure, you can't really do a resonance structure because there's no like lone pairs to give around. I'm not sure if this is like a real resonance structure, but maybe like something like this. That would make the carbon so unhappy. Now, there's no way that you could do a resonance structure because then the carbon would be bonded to 5 things. And I always remember that if carbon is bonded to 5 things, like if it looks like this, if your carbon looks like that, it's going to explode, is what they say at SARC tutoring. So yeah, never bond your carbon to 5 things. And then identical compounds is what these are. The carbons are bonded to the same things all over. It's kind of just like shifting it like in or out of the plane. Cool?
Wait,
oh, you can go. My bad.
Sorry. I just want to know if you're recording this.
I am recording this. I'm going to post it on my YouTube channel, which is like weird, but I'm doing it for you guys. Like, comment, and subscribe.
Turn the notification icon.
Yeah, turn your post notifications on so you know when I post a video. I actually have some videos on there from like a couple years ago. So I was like, don't make fun of me or look at them, please. So are you guys ready to move on to the next question?
I just have a question. So on the other one, you move the chlorine from like the bottom to the top, and then those are identical, right? But then when I look at the one that you drew for like the constitutional ones, I'm still confused because like you moved it too. So I'm like,
so over here, something about constitutional isomer or identical compounds is that when you write them out in that formula that looks like this, so like the one for this one would be CH3, CH, CH3, CH2, C, CH3, CH3, Cl. It's the same one for this one and for this one, for like this one and this one. They have this same formula. So if it helps you on the exam, you might want to write that out and kind of just like break it down like that. So like over here, we have our CH3. Over here, we have our CH3, our CH, our CH3, our CH2. It looks like super messy now, I'm sorry. We have our C, and then we have our two CH3s, and then we have our Cl. It's the same one for both of them. So identical compounds have that same identical, like writing it out kind of like naming thing, whatever this thing is, which you guys have probably done like a bunch of these questions for Alex.
Isomer. Oh, okay.
And then for constitutional isomers, it would look different. It would look like this. It would be CH3, CH, and then in parentheses, we would have our Cl, and then we would have CH2.
Oh.
We can see that constitutional isomers have a different connectivity of the elements, or whatever like the definition is. Does that make sense?
Yeah, thanks.
Okay, cool. And we know with resonance structures, same connectivity, and then there's a difference in the electron shifting. Cool.
Mm-hmm.
Okay, awesome. So we guys also might have a question like this, saying like identify the, he might ask Bronsted-Lowry acid or base, but I feel like Bronsted-Lowry acids and bases are kind of like easier to identify. So he'll most likely ask like Lewis acid. And then let's say that we have something like this. I remember when I took the exam, he had like a question where we actually had to write it out. So that was like super hard for me because I didn't really like go over like how to draw arrows at all before I took the exam. Honestly, guys, I did not do very well on my first Orgo 1 exam. But after that, I got it together because I was like, we're getting this A. And then after that, it was like A's and like high B's from there. So take it from me. Even if you guys don't do well, there's room for redemption. Okay. So, let me see this. Okay. Cool. I don't have a minus charge on it like that. Okay. Awesome. So then it's saying identify the Lewis acid. So let's go ahead and define Lewis acid. Who wants to tell me what they are, what the definition of a Lewis acid is? I know I just wrote it out, but like.
Electron acceptor? Electron donor?
Donor?
It can accept the lone pair.
So I have some mixed. So I have a lone pair acceptor. Is that what we want to? Final answer?
Electron pair acceptor?
Yeah, so electron pair acceptor. Awesome, guys. And then this one is going to be electron donor. The way I remember that is because of Bronsted-Lowry. We have acids and bases, and we know that when we donate a hydrogen, then it makes something more acidic. That's just like based on like bio 1 stuff. So if you're like donating, so like obviously the acid will be donating an H+, and then the base will be accepting the H+. So then over here between Bronsted-Lowry and Lewis, this acid is donating and this one is accepting, and that's literally, if you remember one of them, then you'll just know the other one because you know the like inverses. So over here, let's kind of just try and draw what this structure would look like. So remember that negative goes to positive when you're doing lone pairs. So we can see that this is an ethyl group being added on to the oxygen. So we know that the oxygen is going to be the thing that's like giving the electrons. So we have it on that carbon there. So then we have 1 carbon, 2 carbon. Over here we added on 1 carbon, 2 carbon. So then we're good to go. And then this like bond right here, we can see that this I use iodine, I think. It gains some electrons. So that's where this bond right here is going. It's going to that iodine. Cool. So then that is what we have. Over here, this is what is donating the electron. So then this is going to be our Lewis base, and then that would be the answer to our question. But if we wanted to keep going, this is our Lewis acid. This is our conjugate. Conjugate acid. And then this is going to be our conjugate base. Is everybody good with that?
Yeah. Can we do another example of that one?
We can do another example, but we have an hour left. So it's up to you guys. Do you guys want me to do another example?
No.
If we have time at the end, I can do another example. I'll probably stay until like 6:15, just because I was like a couple minutes late. But yes, are you guys ready to move on? If we have time, I'll do another example like this.
Okay.
Okay, cool. So let's say that we have a question like this. It says rank in order of increasing water solubility. So this is one of those solubility questions. So over here we have an OH, so I'll let you guys think about if we think that one is going to be soluble or not. Over here we have a Br with all of its lone pair goodness. And then over here we have a double bond O. And so let's like number them 1, 2, and 3. Which one do you think is going to be the most water soluble?
1.
1.
Yeah, awesome. And then what do you guys think after that?
The double bonded oxygen.
So you guys think it's going to be 3?
Yes.
Yep.
Okay, awesome. And then obviously the last one is going to be 2. Everybody understand that? It's kind of just, I guess like, it's just like polarity questions. So like the oxygen, it's more polar, and I guess it kind of like has that option to, like this bromine here is like super content. It's kind of just like, that's what I like about Orgo compared to like Gen Chem, is that nothing happens for no reason. So kind of just like in water, this bromine wouldn't really want to, so obviously this like carbon chain here is what's like non-polar, and we know water is like polar. So we kind of have to think like which area between this is going to be the most polar. And obviously we have a water molecule, looks like this, where the hydrogens have a partial positive charge on them, and then oxygen has a partial negative. So we'll see that this like oxygen here will have a higher likelihood of grabbing onto a hydrogen like that compared to the bromine, which like it has its octet. Like the bromine is so happy with where it's at in life, whereas this like oxygen could maybe do something where like this lone pair goes over here and then it grabs onto the hydrogen. So then at the end of that, we would have something like this. So does that like kind of make sense? This one would come from that. Whereas like bromine would just like not do that. Bromine would like have a higher likelihood of leaving as like a leaving group, which you guys will like learn about more later on. But that's kind of just like a polarity question. And 2 would be water soluble just based off it being polar, right? 2 wouldn't really be as water soluble as 3 though. So then we can see that our ranking is like 2, 3, and then 1. But yeah, I guess based on polarity, because it's like grabbing onto those electrons. So like bromine is more polar. I guess it does have like a dipole moment. Does that make sense? We can do a dipole moment question if you guys want right now.
Yeah, could we?
Okay, yeah, awesome. So this is kind of just like what that question would be. It would be 2, 3, 1 as our order. And then over here, let's say, which of the following would you expect not to have a dipole moment? So I found questions like this on the exam. So I guess he would have, it look like this. So like 1 CH2 Cl, 2 CH3 Cl, and then 4 CCl4. I find questions like this so difficult just because I would have to like draw them out, and then you have to like think about it being in like the plane and stuff like that. So this is like when he was like really encouraging having like a molecular kit and stuff like that, which I know he asked me in lecture like where I got my molecular kit from. I got it from Amazon for like $20 and I never used it. It's kind of just like if you draw it then you'll be able to see it. I'm like one of those people. So if we were to draw this one, we would have the C, and then it has 2 hydrogens on it. So let's go ahead and put one of them in the, or like let's put like both of them in the plane like this. Or actually, let's do this. Let's have our Cl over here, and then our other Cl over here, and then let's have our hydrogen like this, and then our hydrogen like, actually, let's not do that. Let's do this like this, and then our Cl and our Cl. Oh, sorry. And then our hydrogen. Well, actually, the chlorine would be on a wedge because it would have priority, which you guys will learn about later on when we're learning about RNS configuration. But let's say that this one looks like this, and then this one looks like this. So there's only 1 chlorine on it. So this question is asking which one will not have a dipole moment, so no dipole.
Do we need to know how to like draw these?
It's not really so much drawing, it's just like knowing that there's going to be a wedge, a dash, and then 2 of them will be in the plane. And we know that this area here is able to have like free rotation because it's an sp3 carbon.
Okay.
Yeah, so dipole moment. And then over here, we have a carbon with a Cl, and then we have another Cl, and then we have another Cl, and then we have another Cl. So then of 1, 2, and 3, let's say our options are A, 1 and 3, B, 2 and 3, C, only 3, D, 1 and 2. And then he probably will have E on the exam. Only 2. Or only 2. So what do you guys think that the answer is? A, B, C, or D?
Wait, is it asking which molecule isn't polar?
Yeah, so it's asking which one is not polar, or like which one will not have a dipole moment.
Is it only the third one?
Oh my gosh, it says 4. Oh, a disaster. I'm sorry.
Yeah,
Was that like confusing you guys? So I have a vote for only the third one.
I think it's A.
Yeah, I think it's only the third one.
Yeah.
So I have Yeah. Okay, so let's go ahead and break this down. So if we were looking at number 1, we would see that the chlorines would obviously be pulling on those electrons. So then I don't know why I put that in quotation marks. They are electrons. But over here it would be pulling on that. So then this one would have a dipole moment. This one, obviously the chlorine is just pulling it forward. Nothing is even like able to pull it in or out of the plane. So then this one is polar. And then with this one, these two are in the plane and they're pulling it in opposite directions. This one is in the front of the page and then this one is in the back of the page. So they're all pulling on the electrons equally because they are the same element. So over here, this one does not have a dipole moment. And I feel like if I were taking the exam, I would say that it was A, just because I'm like, oh, well, if this one is able to like be in the plane, then something like this can happen where the chlorine is just over here and then the hydrogen is here and then they're pulling it in opposite directions. But you have to remember that this here is able to rotate. So the chlorine is like, oh, sorry, this would be a hydrogen here. This one is able to like go to like the least, to like the dash or the wedge. It just has like free rotation because it's an sp3 carbon. Cool.
So what's the answer? Just 3?
So the answer is going to be C, only 3.
Oh, okay. I couldn't see. I thought there was no just 3.
Yeah, awesome. So Dario, thank you for explaining it. They said that the dipole moment cancels out since all of the chlorine surrounding and pull it in the opposite direction. So yeah, that's exactly what's happening. Does that make sense for everybody?
I'm sorry. I'm still kind of confused.
Sorry, go ahead.
I'm sorry.
I'm sorry.
Say that again, please.
I'm still kind of confused on this topic. Why is it only 3 that doesn't have a dipole?
Because the chlorines are just pulling it. So like this one is pulling it up, this one is pulling it down, this one is pulling it behind the page, and this one is pulling it like forward. It's kind of like 4 people tugging on. Let's say that you have like a rope and it's tied like in like a cross like this, like a plus sign, and then everybody's pulling on it equally. So then it'll kind of like form a right angle between it, right? I guess that's like a really bad way to think about it because technically, since it's like tetrahedral, it has a 109 angle, not 95 degrees. But let's just say that everybody's like pulling on it equally.
Okay.
Then they're all putting like equal force on it. So that's as far as my analogy goes. But yeah, it's kind of just like everybody's putting equal force, whereas if you're doing this one, then only like one person is picking it up from the top. And then if you're thinking about like 1 and 2, one of them is pulling it from the back and then one of them is pulling it from the front. You can kind of think of the chlorines as like people pulling on the carbon atom. Does that kind of make sense?
For the first one, did you switch the chlorine and the hydrogen again?
I did. I was kind of just explaining why, even though I was explaining how like number 1 does have a dipole moment, even though like even if it was in like that, because I was saying like if I were taking the exam, then I would be confused, like because they can just be pulling it from the top and the bottom, but you have to remember that this one has free rotation, so it can just like rotate whenever it feels like it.
Okay.
Cool.
But if it were to rotate, do they not all rotate at the same time?
So the thing is like it can rotate and it will, I guess like in space, it'll just like rotate whenever it wants. So because it has the ability to rotate, it does have a dipole moment.
Okay, deal.
So yeah, 1 does have a dipole moment, 2 has a dipole moment, and 3 does not. Cool. I know it's like a little bit confusing. You don't need to know how to draw anything. He might ask you like, which of the following is like the molecule or something like that. But I honestly doubt that. If you're drawing anything, it's going to be like a nomenclature question or like IUPAC, and then it's going to be like, what is the, I'm trying to think of like what the nomenclature was, like which of the following is 1,2-diethyl-4-methyl-cyclohexane.
How would we draw stuff online?
Did he say that you guys were going to draw stuff?
I don't think so. I think it's multiple choice and maybe fill in the blank.
Yeah, he said there is no actual drawings.
Yeah, so he said there was no actual drawing. So then, yeah, the dipoles in one do not cancel out because this one can also look like this. Nitrogen with a chlorine. And this is actually like the more stable conformation for it because the chlorine is on a dash. And we'll learn later that you want like, you'll just want your chlorine to be on a dash because it's like, it's like has a higher priority. It's not going to make sense. Anything that I'm saying right now, it's not going to make sense until probably like the next block, but it has a higher priority. So just remember that it can look like this also. Because this bottom part here, can rotate freely. Okay, so are you guys ready to go over next question?
Yeah, I'm sorry, I do have one more question about this one. So you said that for the first one, it can rotate freely, and that's why it has that. How do you like know like what can like rotate and what can't? So like how do we know like the third one does or does not rotate?
So we know that sp3 carbons have free rotation on them. So like let's say that this is our carbon. Let's just say that these are like all hydrogens. And if they were all hydrogens, would it have a dipole moment?
Yeah, because it's all just like pulling away.
So it would have a dipole moment or it would not have a dipole moment?
It would not have a dipole.
It would not have a dipole moment, yeah, because it's all equal pulling, so there's like equal distribution of the electrons. So this one has free rotation around the bottom area. We know that if we have like a carbon bonded to a carbon, let's say that we have like chlorine and hydrogen and chlorine and hydrogen, this one also has free rotation about the double bond. So then we can have something like this, where we can have cis or we can have trans. And trans just means like they're on opposite sides of the double bond. And then cis means they're on the same side of the double bond. Again, that'll be important later on. Whereas if we have something like this, why do we draw the sp carbons like that?
Because they're unable to bend if it's triple or double bond.
And Dr. Dowdy said something specific in your lecture. Do you guys remember what it was?
Because they're sp2.
Is it because of the carbons?
Why do we draw the double bond like that?
Oh.
Or why do we draw the triple bond like that?
Because there's carbons on both sides.
They're linear, so it's a 180-degree angle. So
yeah, there you go. Because it's linear, so it's 180-degree angle. I feel like that's also important for this exam if you guys just want to like know that. But I'm pretty sure that one like does not have free rotation, does it? If it does, you would have to like kind of like rotate the entire molecule. I'm pretty sure like this doesn't have free rotation. Don't quote me on it though. But just know that with like sp3 carbons, there's like free rotation on that bottom area where it kind of just like can spin. Cool. Okay, so if it's able to spin, then it can, and if it can switch between like the area like here, here, and here, then it might have a dipole moment. So just like take into account how that area is able to have free rotation. Cool.
I'm sorry, can you explain what you said about the linear again? I didn't catch it.
The reason that we draw, I guess that's like not correlated with this, but the reason that we draw it in a straight line is because it has a 180-degree angle like this. So it's like 180 degrees. I don't know, maybe he might ask a question like that. I feel like he mentioned it in lecture like a couple times, or like once. I feel like it was important for when I took the class for some reason. But anyways, yes. Is that cool with everybody to move on?
Yeah.
Okay, awesome. So he might also ask a question like, which of the following is the least stable conformation? Conformation. So then over here, now we're going over the fun stuff, which I didn't learn how to draw these. I mentioned this in like one of the groups that I visited when we were doing like the worksheet in class, how I didn't learn how to draw these until like literally the day before class, or the day before the exam. I was putting it off. I did the same thing with, what is it called? The chair conformations, which honestly didn't do me very well for the first exam. I should learn from my mistakes, which is why I'm kind of like doing the review today, because I want it to be like easier on you guys, I guess. But you guys like aren't just like the day before the exam, like, oh shoot, I don't know what to go over. Okay, so we're almost done drawing this last little. Okay, so between 1, 2, and 3, which one do you guys think is the least stable conformation?
Maybe 1.
3.
2.
3.
So I have answers 1, 2, and 3.
1.
Okay, least stable conformation.
Wait,
So
no,
like,
least stable, just kidding. 2, that's right.
okay, so now I have a lot of votes for 2, and that is correct. So over here, we know this one is going to be least stable because we have heavy groups, is how I kind of like understood it as. We have like heavy groups overlapping on top of each other. Over here, number 1 is going to be the most stable, because this one kind of just has like a lot of like buzzing around the electrons. You have like 2 lone pairs, and that's like really far away from this one over here. So like this one is doing its own thing, and that one is doing its own thing, whereas over here, they're kind of like all up in each other's business. So that's why that one is the least stable. And we know that molecules are constantly trying to gain stability. So the molecule might like rotate into the first one. So if we were going to like rank from like least stable to most stable, and the answer would be 2 is the least stable, and then 3 is like medium, and then 1 is the most stable. Cool?
Yeah, question on that though?
Yeah, what's up?
Is 3 the same molecule as the other 2?
Yeah.
Because those hydroxides are attached to.
My bad, you guys. You caught me. I'm so sorry. Okay, there you go.
Hey, nice.
I guess it would still kind of just be like the same thing.
Okay.
We'll
Yeah, it's the same
draw
idea.
one.
I just got confused with it.
Yeah, same idea of like where the distribution is of electrons, a different molecule. So that would look like this. And like this one like doesn't look like that. Okay, so maybe we can draw one of those if we have time. So are you guys ready to learn how to do chair conformations, hopefully in like a simple way?
Yes.
Yes, please.
Okay. Hopefully in a simple way. I was explaining this when I was doing the worksheet with people the other day, and they were like, I just like don't understand what you're saying to me right now. So I like to draw my chairs like kind of like starting off like a bow tie. Don't judge them. They're not the prettiest, but it is what it is. You know what I mean? I'm just gonna like prepare my chair conformations like this. And he was talking about like ring flips and stuff like that. I honestly don't expect him to test you on ring flips. But he might. So like be prepared for anything. Be prepared for the worst. So over here, let's say that we have 2 axial ones that are 1 carbon away. That's gonna make them trans. Let's say that we have 1 equatorial one and then an axial one. and they're like a full carbon away, that is going to make them also trans, but that's actually not the one that I want to explain to you guys. Let's say that we have two equatorials. I'm actually going to make the equatorial ones in blue. So let's say that we have two equatorial ones next to each other. That's going to make them trans because just kind of like if they're in the same conformation and they're in the same, like 1 carbon and 2 carbon, then they're going to be trans. Let's see, do I have any other trans ones? Let's say that we have an equatorial one at this carbon, and then we skip over a carbon, and then we have an axial one, and that's going to be trans conformation. So like we can have cis or trans, and that would be trans. And then over here, let's say that we have an axial one and then an equatorial one like this. That's going to make them cis. Let's say that we have an equatorial one and an axial one, which is literally the same thing as the other one over here. That's going to make it cis. And then let's say that we have 2 axial ones far away from each other. That's going to make it cis. Does that kind of like maybe help a little bit as like breaking it down maybe?
I'm just confused on how to determine when they're trans or cis.
I don't know if he would necessarily have you determine. He might ask a question like, which of the following is cis 1, 3? Okay, so do you guys have this copied down so I can move on to the next page and then we can try and do one?
Yeah.
Yeah.
Okay, cool. So let's say that he's asking for, like, which of the following is cis 1, I guess we would say 1 ethyl, 2 methyl cyclohexane, and let's say that we have like this as our options. So we have like this one and this one, or we have this one and this one, or we have, so like this would be, I guess it kind of like depends on how you're going, how you're numbering them. Okay, and then let's say that we have like this one and this one. So what do you guys, choose your fighter? You guys think that the answer is 1, 2, or 3? I feel like, I think when I took the exam, he had us actually draw it out, but obviously you guys can't draw anything out, so he would probably have the question like structured like this.
2.
So I have a vote for 2.
I think it would be 3.
I have a vote for 3.
2.
I think it might be 3 too.
Okay, so we have 2 votes for 3. I think I have 2 votes for 2. So we're kind of like tied. I'll give, who wants to be the tiebreaker? Don't be shy.
Is it 2?
Put some more. Okay, so I have another vote for 2. Okay, so right off the bat, we can see that this one would be like considered like 1, 2, and 3. But over here, we're asked for 1 and 2. So we know that it's not 3, because although this is cis, because they're 1 carbon away, this would be like 1 ethyl 3 methyl cyclohexane, but we're asked for 2. So you got to pay attention to like every single little thing over here. And then the conformation here, because they're both cis, is going to be trans. And then over here, even though it's kind of like backwards, we would have 1 and then 2. So that is technically correct. And then because they're opposite, so we have like an equatorial and an axial, this one is going to be cis. So we have our answer here is going to be 2. Does that make sense for everybody?
So what makes the first one, like, how can we differentiate between the first and the second one?
So this one is two cis ones, cis and cis. This one we have an equatorial one.
Okay.
So we have two different conformations.
Is cis also axial? Is that the same thing?
No, cis is not axial. Cis is like the difference in the two conformations. So like like this one. I'm not really sure how to explain it like past this. So like over here, we have an axial one. And then these blue ones are supposed to be equatorial. And the other one, I wasn't making them red and blue like for that. I can't really like, Brianna's asking, so it's just like if they're both going up or both going down, and then trans is one up and one down. Not necessarily, because over here, we can see in this one, trans, both of them are in equatorial. It kind of just depends on where they are on, like, it depends on like where they are. Does that make sense?
So there's not like specific trends for like a cis necessarily that we can like memorize?
Okay, wait, give me a second. Is it cis?
I think like when I went to like today Jessica's office hour, she said that cis and trans are only dependent on their direction. So if they're both like pointing upwards, even though the one is axial and one is equatorial, they're still cis, even if like they're different positions.
I'm sorry, you guys. These are trans. I'm so sorry. These are going to be trans. And then this one is going to be cis. I don't know why I drew it like that. And then this one is going to be trans, and this one is going to be trans. Sorry about that. I literally just like completely flipped it for you guys. Does that make sense? I'm so sorry. So it's 1, 3 when you're dealing with 2. Why is the last one trans? This one is going to also be cis, maybe. Oh, now I'm confusing myself. Is there one carbon away? We'll get back to this if we have time. I would Google it. I'm second guessing myself currently, but I'm going to try and get back to you on this, okay? If not, I'll like edit a little like bit onto the little video and then get back to you. Is that cool?
Yeah.
Okay, I'll get back to you on this. I'm going to actually clear this page. Ignore what I was saying for the last little bit. We're just gonna start a new page. Okay, we're gonna clear all the drawings. Cute. Okay, we'll get back to this one. I'm so sorry. Do you guys want to do functional groups, or do you guys think you can do the functional groups on your own time?
I feel like we could memorize that on our own time. Like,
okay, cool.
Problems or
Can you just tell us like which ones are important that you recommend, like, for sure?
The ones that are important, I would know aldehyde. I would know ketones, carboxylic acid. I would know esters. I would know thioester. I would know amides. I would know alkyl halide. I would know alcohol, ethers, amine, sulfide, disulfide, and thiol.
What's a thioester? Because I don't remember seeing that in the lectures, and it's not on this thing we had to order online. It's like Orgo Chemistry Fundamentals.
Yeah, so that is what a thioester is. Theo just means like it's an S, like a sulfur, instead of something like this. actually just going to draw them in really quick. Super fast. So this is like an NH2. And this is like an alkyl halide is like the halide, which is like the one over from the halogens. Alcohol is when we have as the sp, I believe it's an sp3 carbon bonding to an OH. Ether is like that. Amine is like an NH2. Sulfide is like an S, like that. And we know sulfur is like the same thing as like oxygen, where it wants like 2 bonds and 2 lone pairs. Disulfide is something like this. And then thiol is like that. Cool. So those are the functional groups I would know for your exam. Cool.
Yeah, thank you.
Okay, awesome. I'm gonna clear this page. Actually, I'm gonna clear all the drawings. How do we do that?
Just to be sure, we should like memorize all of those for the yeah.
Yeah. So over here, let's say that he's saying like name this compound. I don't know how like in detail he's gonna go for naming compounds, honestly, but like I feel like something like this is pretty decent. So obviously first thing, find the longest chain and like see where the substituents will have like the lower number. Like, are we gonna start from this side or the side?
The left.
Yeah, so we're gonna go left to right. So then we're gonna have 1, 2, 3, 4, 5, 6, 7, 8. Did I count that correctly? Okay, wait. Yeah, I did count it correctly. So over here we want the substituents to have the lowest number on them. So if we were to do it the other way, then our first substituent would be at 1, 2, 3, 4. Would be like 4, like 6, and 7. Whereas if we do it this way, then we have substituents at 2, 3, and 5, which is better than 4, 6, and 7. Yeah, and then the substituents are like the branches. So over here we have 8, so that's going to be octane as our ending. At 2 we have a methyl. At 3 we have a methyl. And then at 5 we have an ethyl. And then we do it from what is it called? Like alphabetizing it. So E comes before M. So we're going to have 5 methyl. And then we're going to have 2, 3 dimethyl. Oh, sorry. Ethyl. Yeah, thank you guys. Dimethyl octane. Is that cool with everybody? And that's kind of just like a good way. Kind of with these, it's just practice. I like to do it like how I just showed you guys, where I like break down where the substituents are at what numbers. Another kind of question he might have, which I know is like really annoying at this point, because you guys are probably like, I hate anything that's circle, because it looks like really hard, but honestly it's not like that difficult if you guys kind of just like break it down. So over here, our longest chain is going to be this cyclohexane. And we know that it's cyclo because it's like cyclo just means like it's an enclosed structure, I guess. And then hexane means 6. So over here, 6 carbons. And then finding out where to do like start numbering with cyclo structures is kind of like hard. I kind of just like test them out. So like we can have this option where we have like 1, 2, 3, and 4. We can have this option where it's like 1, 2, 3, 4, 5, 6. That's like a really bad option. We can do this one, which is like 1, 2, 3, 4, 5, 6. That's another pretty bad option. I think that yellow is like the safest bet. What do you guys think?
Yeah.
And we really wouldn't start at the methyl just because we already know that that one is going to have like a gap between these two. So that's obviously not going to give us the lowest substituents. So yes, yellow is like our safest bet. So then for this one, our answer is going to be 1,2-diethyl 4-methyl cyclohexane, and then cyclohexane is one word. I just like couldn't fit it over there. Is everybody good with that?
Yes.
Okay, cool. Another question you might have is a formal charge question. On the exam when I took this, I like really overthought my formal charge question. And I was like, okay, well, nitrogen will give 5 electrons, and then oxygen will like have like this many electrons. It's really like not that deep. He just like wants to know what the charge is on here. So when you guys think that the charges on this nitrogen, and he's not going to give you lone pairs, you're going to have to write those in yourself. So over here for the oxygen, what is our charge?
Did you draw the lone pairs on the bottom? I can't like
I did. I drew the lone pairs for the oxygen like on my own.
So would it be 0?
0.
Yeah. So then over here, we know that oxygen wants 6 electrons. We have 4 electrons being shared in these bonds, or yeah, we have 4 electrons being shared in the bond. So like 2 electrons are in each sigma bond. So like this is a sigma bond. This is a pi bond. And this is also a sigma bond. So like there's a sigma bond and a pi bond and a double bond. And then so yeah, we have 4 divided by 2, and then plus 4, I believe, yeah. And then that'll give us a formal charge of 0. That's just the formal charge equation. And then over here for nitrogen, nitrogen wants 5 minus 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So over here we have 8 electrons being shared divided by 2. And then that would give it a positive charge, but there's going to be more electrons in there to give it a negative charge. So then just because that's how like NH2 would be written, I guess. So then over here it would also have those 2, and then we would have a formal charge of -1 for nitrogen.
But so how would that work if it has more than 4, like it's already bonded 4 times? So wouldn't that make it the 5th, or does it not count there?
What do you mean for that?
Like, wouldn't it just be a positive charge on the N? Because it already has the 4. Like,
so
as
I guess in this one, I guess I was right to like go in and count how many electrons there are. So like oxygen would give 6, the carbon would give 4. I guess like maybe he just like wouldn't have the option as +1. He's gonna like give it as like a straight answer. Like the answer would either be +1 or -1, or you would know like if it would have a minus charge on there. If that makes sense.
Can't nitrogen not have 10? That's what my question.
Yeah, that's more than an octet there.
Yeah, so it kind of.
It should only have 6.
Yeah.
6. Sorry, 4 sticks coming out of it, like 4 bonds instead of that lone pair.
That is true. The correct answer is -1 though. It just is. Like.
Why would it not be positive though? Even if it is.
I guess it does have more than its octet. Nitrogen is one of those weird ones. I guess that's like what I can say for you guys. Let me try and do another.
Like for it, when nitrogen has a -1, isn't it usually it has 2 bonds and 2 lone pairs?
Yeah, like nitrogen can look like this.
Yeah.
Or to have a negative charge on it, because then it would have like that extra one. In this case, the answer is just -1. Like I really can't explain it pass that. Let me try and find another example for you guys. I know I have another. Okay, so let's do this one. Let's see. I'm gonna clear this one. Am I good to erase?
Yeah.
Okay, cool. So let's say that we have a boron bonded to a nitrogen. And it looks like this. So we have an NH3 with a bromine. And then we have another bromine. We have another bromine. And it's saying, what is the charge? What are the formal charges of nitrogen and boron respectively? So for nitrogen, what do we think the charge is going to be?
+1.
Okay, so it's going to be, has its octet divided by 2 plus 0, and that's going to give us +1. So then we're going to have a +1 charge on our nitrogen. And then does anybody know about boron? How many electrons that one?
-1.
Yeah. Yeah, so the charge on boron is going to be -1, but do you know what the actual equation is going to look like?
Is it 3 minus 4?
Yeah, so then we're going to have, that's bonded to 4 things divided by 2 plus 0. And then from that, we're going to get, I guess, 8, sorry, my bad. Again, we have our 8. So then that would be 2, so like 3 minus 4, and then -1. Cool. Sorry, when I do like mental math, it like just, well, like it confuses people. Like maybe let's say that our options are like A +1 and -1, B -1 +1, C -1, 0, and then D 0 and 0. So what is our answer? For nitrogen and boron respectively.
A.
Yeah, the answer here is going to be A.
Would we get the same answer if we used the number of valence electrons minus like the number of sticks and dots one? Would we get the same answer if we use that?
That's how
I
find it the easiest way. Like that's how I noticed that the nitrogen had the wrong charge on it. Because if you add the lone pairs and then the number of bonds and subtract that by the valence number, you'll get the charge on it. So for example, the first nitrogen, since it has 4 bonds to each of the B and then the 3 H's, that's 4. Its valence number is 5, so you'll do 5 minus 4, which is +1.
Yeah, that's what I did too, and it's a lot easier.
Or you could just think of each little line bond is sharing 1 electron. So it's got 4 electrons being shared and it needs 5. So you do a +1 because I need 5.
Yeah, it's whatever works for you. This equation is kind of just like foolproof most of the time. So it's kind of just like what works for you. On the exam, like personally, I would want like a foolproof equation, not like, oh, hydrogen wants 1 bond to it or something like that. This is like nitrogen wants 5. He has 4 bonds with it, but that's 8 electrons divided by 2. Because imagine if there was like a lone pair in there. Then you're like, oh my gosh. Then it's just -1. But that's like a 10 or whatever. That's not a thing.
So wait, did we know that the last one had a lone pair before? Like, remember the last N had a lone pair and it had 4 bonds. So it was -1.
I erased it, but I guess like there was a lone pair on there. I think he wrote it in there.
Okay, all right.
I guess like on the in the question, it probably had the lone pair.
Okay, and that's when you would know. So like if it didn't have that lone pair, you know it'd be +1, and with the lone pair, it'd be -1.
Yes, cool.
Okay.
I have a question.
Yeah.
Are we allowed to, like, legally, I guess you say in this class, talk about like old test questions?
I wouldn't recommend it.
I'm not pointing any fingers. I'm just asking before I say anything.
Yeah, I just like wouldn't recommend it.
Okay. I just wanted to make sure. Yeah. Okay. Cool. Thanks.
Okay. Awesome. So, you can ask me a question and not tell me it's an all test question, and then I can answer it unknowingly. Cool.
Can I ask a,
cool, thank you.
Sorry, can I ask a question about the practice quiz from yesterday?
The practice quiz, was it due already?
Yes, it was already due.
Okay, then yeah, sure.
So I know one of the questions was asking about the ammonium ion and the charge on that, and you just kind of like have to know that. Are there any other like things like that that we should know and like put into our memory before the test?
Ammonium is NH4 plus, right?
Right, yeah. Yeah, that question just
have...
kind of like put me off guard, and I didn't know if there were like other ones that we should know.
Wait, such a good question, Ashley. I was thinking the same thing when I took it. I literally said it into my camera. I was like, are we supposed to freaking know this? Like,
I don't really have, he wouldn't really ask like specifically like what's the charge on ammonium. He would maybe have like, I feel like anything with like like nitrogen in it like really throws me off, because there's like NH3, there's NH4, there's NH2, there really is an NH, but like there's just like so many different like N bonded to H molecules that it's like hard to keep track of it. But I feel like ammonium is the only one. It's kind of like more like a gen chem question to ask like what's the charge, you know what I mean?
Yeah. But we didn't have a periodic table either, so I was sitting there and I was like questioning myself too, and I was like, wait, is it NH4? Is it NH3? And I was like, guess I don't know.
Yeah, I feel like ammonium is the only one, but look at the book and see if there's anything like with like naming compounds that are like things that you should know for naming compounds, and I feel like that would like help maybe.
Thank you.
Cool. Yeah, no problem. So over here, let's say that we're doing Newman projection for this. Somebody asked, does anyone know if we can have a scrap paper on the exam? Yes, I'm pretty sure you can have a scrap paper on the exam.
You
just
can.
like I was saying at the, you can't?
You can.
Okay, yeah, you can. And then at the beginning, just make sure that you show the front and back of the scrap piece of paper, and also show the front and back of your periodic table.
Also, don't look down a lot, because it'll...
Yeah, try not to look down a lot, but like, if you do look down and it flags you, then he's just gonna look at your like recording and just decide if you were cheating or not, and hopefully you weren't cheating. So yeah, just like don't cheat on the exam.
Really quick about this, is it listening for sounds? Like if they're like, if someone like shouts or there's a loud noise, is it gonna flag me for sound?
I think it might. I know that in one of my other classes that we're using the lockdown browser, people were saying like if there is like a really loud sound and you're scared that you're gonna get flagged because of it, just mention something like, oh, that was my like roommate like slamming the door. But like I feel like that would distract me, so I'm not really sure. Maybe like when, like I was saying in the group meet, I would like take a picture of the scrap piece of paper at the end of the exam and send it into him just to show him like what you were writing during the exam. Maybe mention like during my recording around like 15 minutes in, my roommate walked in and I had to tell him I was taking an exam or something like that. Or like my parent was like slamming a cabinet and I had to just like say that was a sound.
Okay, thank you.
What if you have like a bunch of siblings and you live in like a small house and you can't really control what they do? And like if like someone sits at the table with you, like I can tell like my family, like, listen, I'm gonna be taking tests, I'm sitting at this table, no one talk. And like they're gonna be like, all right, whatever. And then they were gonna do it anyway.
Are you sitting at the table while you're taking the exam?
Because I think because it's better, because they said I'll take it on your bed, so I'm not gonna like sit on my bed in my room where people would barge in anyway. Because I live at home, so.
Yeah, that was the same thing for me. I was like, I can't take it in my room now, and like my family lives in my home.
Can you take it in your room, like on Wait, are you not allowed to take it on the floor?
No, you can't take it on the floor, it said. I don't know why.
It's just because you have to show your surroundings. So like there's a lot of things that can be on the floor or like on your bed or anything like that. I personally took it at my desk and my class was at like 10 in the morning. So everyone in my house was asleep when I took my exam. So I didn't really have that problem.
My family's all up by 6, so.
Tell them to just sleep in. Just like, hey guys, have an exam.
Man, I try, but they are like, no. I'm like, okay,
Rest
cool.
up, you guys. Your body deserves it.
Will the exam be available all day or only a specific amount of time?
I believe it's only a specific amount of time.
Just during our class time.
Gotcha.
What if we need to like use a different piece of scrap paper because we ran out of room on the first one?
I have a couple pieces of scrap paper, but honestly, it's 25 questions. Like, how much scrap paper are you using? But if you do run out of scrap paper, maybe have 2 sheets, but make sure you put them both up, like for the exam. Cool. Is my recommendation.
I have a question.
Does the score come out right away? I'm not sure. I know for my class, the professor had it. So actually, the professor didn't have it muted for a little bit, and everybody who got flagged didn't get their scores. So there were like half the class got flagged. So like half of us didn't get our exam, and we're all like, oh, we're gonna get a 0 on this exam. But then our grades like came out after like a day or something like that. But I don't think he's gonna release scores right away, just because it'll like scare people who did get flagged.
If you get flagged, it doesn't give you your grade.
Yeah. So I'm not sure. He'll probably talk about it tomorrow.
If you don't get flagged at all, does the recording go to them?
I'm pretty sure that it goes to them either way. Yeah. I'm not sure. This was my first time using it, was like last week when I had my exam. So I'm not 100% sure.
I have a question. Sorry.
Yeah, what's up?
Questions. When you took your exam for biochem, you said when you show the room, is it just once, right? Or is it just
it's only once at the beginning. And just make sure that you sit down like 5 minutes before the exam to actually like start that stuff, because it does take a while to like show your ID and stuff like that. And once the exam closes, it closes. You know what I mean?
So can you start it before?
I'm not sure. I think I started like doing the whole like scanning my room and whatever like 4 minutes before the exam.
Okay.
And then when I started it, it was like the exam had started like a minute ago. I don't know how sensitive the system is to flagging, but I would imagine that it's pretty sensitive. Like I know a couple of people were like saying like, oh, I was literally just like talking to myself the whole time and it flagged me. I like looked down for 2 seconds.
I like speak out, like I whisper to myself.
Mm-hmm. I also do that. Like I'll like read questions out loud and stuff like that, or I'll like whisper it kind of. Especially if it's like doesn't make any sense. But yes, you guys want to continue? Maybe.
I have a quick question.
Another question. Yeah, what's up?
I'm not sure if you've already addressed this, but in reference to the scrap paper, so when I have scrap paper, like I look down a lot, and I know that some people have said that it'll flag you if you look down. And what did you suggest, like taking a picture of it after and sending it to him?
Yeah, so I suggested taking a picture of the scrap paper after the exam and just sending in sending it on web course, because he only responds to web course, and just saying like labeling it as like whatever your name is, comma, S, scrap piece of paper, exam 1, or exam 1, scrap piece of paper. And I feel like that's like a really solid way to like make sure he knows that you're not cheating.
Okay. But I'm not sure who said this, but if you look down a certain amount of times, doesn't it lock you out?
That's a UF, not here. I don't think.
Okay. It's just, I think because the same system your friend was using, right?
No, it was honor lock. That's what he said he might use for the final.
Oh, okay. Just wanted to make sure. Thank you.
Yeah. I mean, it might. I mean, I don't know. That's not what I've heard about this, but I know that's how it is for honor lock.
I hope not. That would suck.
It kept like popping up the little box because I kept looking down on the scrap paper. It kept like showing up something look up.
But how am I supposed to write it without looking down? I don't know.
And you guys are probably gonna get flagged, but like if you guys aren't cheating, then I just like wouldn't have anything to worry about.
Okay. I guess my
Or,
biggest fear is just getting locked out or something happening. I don't know.
So Cassidy said, I've used Respondus a lot, and I should have been flagged for looking around a lot, but I wasn't. Yeah, so Cassidy has had a good experience with HonorLock, with Respondus. So there's really nothing to worry about, as long as I feel like it can like sense cheaters, you know what I mean? Like if you like get flagged and you're surprised that you get flagged, then that's a good sign. So if you like get flagged and you're like, whatever, I know I was cheating, and continue on with the exam, that's a bad sign. So if you're gonna cheat, like be like, oh, I can't believe I just got flagged. Like, what a shock. That is like proctoring jail. I know a couple of people were like worried about it because it's like taking the exam and like having the professor on the other side of the desk, and maybe if you're like don't know a question, just like look into the camera and be like, please, and then continue your exam. But yeah, so I drew up a couple of questions while we were having a grand time discussing the pain of Respondus. So this is like a resonance question, drawing resonance structures, like how pretty. And then this is a Newman projection. As you can see, this is the front carbon, and you can, I can imagine myself looking at the molecule just like this. So because the chlorine is on the left, I know that like if I were looking at it, the chlorine would be on my right. I just know, I can just feel it. And then the hydrogen would be on my left. Is that what I don't know, my left and my right. Chlorine on my right, hydrogen on my left, and then the other carbon is like back there again, bromine on my right, hydrogen on my left, and then that ethyl is going to be sticking up like that. This circle in the back represents the back carbon, and the circle in the front represents the front carbon. And I didn't learn that again until like a couple days before the exam, and I was like, oh my god, I didn't even know what that circle meant. But it's the back carbon, so that's just fun fact, you guys. Actually not a fun fact, I would know that before going into the exam. So yeah, know that the equatorial position is like more stable. So if we had a question like this, I'm gonna go ahead and clear this one. And let's say that we have this.
These like questions that you're like, that you have, is there like a practice exam we could take or something?
It's not really a practice exam that you guys can take. It's kind of just like practice questions that I have from like the book or from PowerPoints. Oh yeah, and also something, the PowerPoints at the beginning that you guys go through during class, when he goes over questions, like, and he like waits and says like, okay, I'll give you guys 10 to 15 seconds to answer this, and then there's always that one person who answers it like after 3 seconds of posting it, like, we get it, you study. But look at those, definitely look at those. That's all I'm gonna say, but look at those questions, because like 50% of the time he'll have those as questions on your exam. So just saying, you guys want those points, get those points, you guys.
Also,
so,
we give extra credit questions. One of the other TAs says he does, but then when we asked him, he said sometimes, I don't know.
When I took Orgo 1, he did give extra credit questions. When I took Orgo 2, he didn't give extra credit questions. For the class before me, he gave extra credit questions. So I'm not sure if he just like doesn't give extra credit questions anymore. Where does he post the recorded lectures? Probably in the Zoom tab, in like the past, and like if you go to the Zoom tab, there's a section that says recordings. And then this is going to be on my YouTube channel, so I'll post a link to the video in the group me. You said those questions are in the PowerPoints, right? Would you recommend going through the recorded lectures, finding those questions he went over? So the recorded, yeah, the Zoom lectures. Go through the Zoom lectures, not the recorded ones, like the, he has these like recorded PowerPoint ones, like narrated PowerPoints, I think that's what he calls them. he doesn't have those like special questions in there. He only has them that you guys like went over in class. Do you think the worksheets are a good representation of things? You might ask on the exam as well. I used to like review the worksheets before class, before the exam, but I never found them like super duper helpful. Like I never saw the exact same questions on the exam. So it's like up to you if you want to review them or not, but he does write those questions. So it's like up to you. If you like have time to go over them, then go over them. But if not, then they're not like the most helpful things to like get 100. Something like really important about classes, I feel like, is just like knowing what kind of questions the professor is going to ask. And Dr. Dowdy really just like likes to ask those questions from the PowerPoint. He likes to ask book questions. Sometimes he'll ask homework questions, like not all the time. But definitely if you guys want to like watch this again and like do these questions on your own, then that would probably also be pretty helpful. Wink, wink. So this question is saying rank the following conformations of a distributed cyclohexane from least stable to most stable. So we're looking from least to most stable. And so this is what I was saying, equatorial position is more stable, like compared to axial. And so the answer here is going to be 4, 2, 3, and then 1. So this one has like an ethyl on it, and these are both axial. So we know that that's going to be pretty unstable. And then like this one has an ethyl, which is making it more unstable than like this one, which also is like 2 axial ones. And then this one has like an equatorial and an axial one. So it's like kind of like the best of both worlds. So we're going to rank them at number like 3. And then over here, this is 2 equatorial ones. So then we know that that one is going to be pretty solid, awesome, fantastic, most stable. Cool.
Wait, so 2 is the second most stable because they're both the same, correct?
Yeah.
Okay.
Or no, 2 is the second most stable. 2 is the least stable. Like 2 is the second least stable.
I mean like
because
not 2 in the order. I mean like 2 once it's ranked, like really the one in the third left corner.
In the third left corner. This one here?
Yes. So why is that one the second most stable?
Because this one has like number 4 is like less stable than that because of its ethyl. So the ethyl group is kind of like throwing it off balance, kind of.
Okay, gotcha.
Cool.
Yep.
Because it's like the same distance between like the carbons. It's just like less stable. Does that make sense? Kind of, hopefully. Not all the way.
Yeah. Thank you.
Awesome. So
also, does our professor write his own exams? Like, is it the same style as the worksheets?
It is not the same style as the worksheets. I feel like the questions that I'm asking here are pretty much pretty similar to his like exam style.
Okay.
But yeah, that's like, I would definitely study this little review, and then yeah.
If equatorial is more stable, why? Oh, never mind. Never mind. I was reading the numbers wrong.
It's okay. Yeah, sorry. I had like I forgot to draw the 2 in there, so I just like stuck it in the corner.
It's all good.
And then did you guys go over like specific rotation of compounds at all? No. Maybe.
Oh, I don't think so.
Did you guys go over chirality questions?
I don't think so.
No, I think that's the next chapter.
Okay, that's the next chapter. It's also weird that you guys are having like a exam that's like 1 through 4, because It's just like kind of is weird. Like when I took it, it was all 1 through 3, maybe because it's summer.
Yeah, I think that's why it's like a little bit shorter.
Yeah. Is this a summer D class?
It's summer C.
Summer C. Okay, yeah. So it's 12 weeks compared to 16. Okay. Yeah, so those are like kind of like all the like example questions that I have for you guys. Is there anything else you guys might want to go over?
Could we do the one more example on the Lewis acids?
Yeah. So this is going to be one of the harder ones. So okay, I guess this isn't a Lewis acid one. This is just like a regular, this is a Bronsted-Lowry acid-base reaction question. I guess we can also do more of CH4 if we can. I think I know what you mean, and I'll try and find a question like that. So let's say that we have this one like this. Then we have like, I'm trying to like think, I'm trying to like make one like off the top of my head now. Okay, let's do this. Do like an oxygen like this, and then this one has a minus sign, and this has a plus sign on it, and then we have like a Br over here. And then, okay, so what do you guys think? Let's say that this is the product of the reaction. Oh my gosh, this looks like a disaster of a reaction, actually. Still a plus sign over there, pretty unstable. Okay, so do you guys want to like go ahead and annotate it yourself? Somebody wants to go in and annotate what the arrows are going to look like. This is pretty similar to the other question we did.
Can you like explain the thought process? I feel like I'm missing, like I'm not understanding the how to go about it.
So kind of just like with drawing the arrows, we have that negative goes to positive. So we know that like this oxygen here is forming a new bond to 2 carbon atoms. And over here we have 2 carbon atoms. So what we're going to want to happen is one of these lone pairs over here is going to come and attack this carbon atom over here. And then this, I guess we can draw it out like this, because honestly, when I took the class, I couldn't even fathom what the line structures were. So let me like kind of try and make it easier for you guys. So over here, this lone pair is going to grab this carbon over here, and then this is made of 2 electrons right here, right? That's what that bond is. So this bond is going to go to the bromine. So then we see 2 extra electrons on the bromine, and that's where it came from. And then over here, we formed a bond between the oxygens and the carbon. So that means that we had to break a bond. So that's like another thing. If you form a bond, break a bond. I guess it's not really related here. It'll make sense more later on, but we'll see that like bromine just like isn't there anymore. So that bond was broken. But we still have like the same number of electrons in our entire reaction, and that's why we have this minus sign is still intact there, and then this plus sign is still intact there. So that's another thing, is that you're going to want to make sure that the formal charge of your entire reaction is the same. So like over here we have a net charge of 0. So we like want to make sure that that's the same. So that's how we'll like make sure that we didn't like add or subtract any electrons. Would Br then react with the C plus? Probably not, because the Br is like really content on its own. You'll learn later on that Br is actually a really good leaving group. So you might see something like if we had something like this, in a reaction, I guess let me do it like this. If we had something like the Br, like that, the Br would actually just like leave voluntarily. Like the Br would just be able to leave. Like without any
Is that
sort of
like the like KOH and the K was like by itself?
That's a little bit different than KOH being on its own.
Dude, I did not understand that one when I was like looking at it. The K was just like alone. And I was like, what?
Okay, let's go ahead and finish this one, and then we can go over that question. So yeah, kind of what this one would look like is this. So we'd have a plus sign, a Br, and then this is our final product, plus sign, plus our Br minus. This lone pair would come and attack this carbon, and then that bromine would leave, leaving us with this. And then we know that since this one is donating the electrons, and this is going to be our Lewis base. This is going to be our Lewis acid since it's accepting the lone pair of electrons. This is going to be our conjugate acid, and the only way I remember that is like it was our base and now it's just like our acid. And then this is going to be our conjugate base. Is that good with everybody? Kind of.
Yeah.
You guys will get the hang of drawing these what is it called? What are they? Drawing the arrows, like it comes with time. So I'm going to clear this and then we can do a one more question like this. So let's say that we have our nice little ketone over here. We have a hydrogen. I'm going to ask you guys what's going to go in this box. This is our nice little equilibrium arrow. What goes in this box? And let's say that we have this. Does anybody want to fill this in? So right off the bat, what do you think if this is an acid-base reaction, which is why we have this equilibrium arrow over here, where do you think this got its hydrogen from?
The first one.
Yeah, the original reaction. So that means that this molecule originally looked like this. Right? We know that. So then this would be our base, and that would be our Bronsted-Lowry base, and then this would be our Bronsted-Lowry acid. Since it's donating the hydrogen, this would be our Bronsted-Lowry base, and then this would be our conjugate acid, since it now has the hydrogen there. And what happened with these electrons is that this lone pair came and grabbed that hydrogen from there, and then put the lone pair on that carbon over there. And that makes sense because that carbon is kind of just like more electronegative than the hydrogen, so it's not going to take the lone pair with it. So then what we have our conjugate base looking like is this. So our carbon has a lone pair on it, and then everything else stays the same. Is that good with everybody?
Yeah.
Okay, cool. Somebody asked, is anybody seeing these types of problems for the first time? Anybody? Is this your first time seeing these questions? It can be a bit overwhelming, but you know, practice makes perfect.
For the last example, sorry, what was the conjugate base for the last one you just did? For the Lewis base and Lewis acid?
I don't have that question written down, and I erased it.
Conjugate base with BR.
Okay, thank you.
I'm only trying to think of what
I'm
it was.
still like not really clear on the difference between Bronsted-Lowry acids and bases and the Lewis acid.
Yes, I don't know why me either. Like if you look at this, how do you know that's not a Lewis acid?
Well, this one isn't it because it like has the hydrogen.
Mm-hmm.
But
so the difference here is that we're dealing with a hydrogen, and then instead of just like dealing with a full-on molecule. So it's not just like dealing with like carbons. Actually, we have like a hydrogen. So that's gonna like change the acidity. I just kind of remember the definition of Bronsted-Lowry acid.
Isn't it?
And that is proton donor.
Yeah.
And then the base is going to be the proton acceptor. And then I know that if we're not dealing with protons, then we're dealing with the electrons. And then in Bronsted-Lowry acid, we have that the acid is a donor. So then I remember that in Lewis acids, the acid is an acceptor. Okay. And then this is a donor. And then I'm able to kind of just like fill it in just by knowing that Bronsted-Lowry acids are hydrogen donors. Or sorry, hydrogen donors. I guess this is like a hydronium or hydrogen ion. Okay. Does that make sense for everybody? Okay, cool. Yeah, so that's pretty much what all of the questions that I have for you guys here are. You guys want me to try and figure out what the chair confirmations are? Like how
I can read the book for that, but I just wanted to say thank you. This was so helpful.
Yeah, of course, you guys.
Yeah, I also want to say that.
Thank you.
Pretty dope, man.
Yeah, no problem. So you guys all want me to do chair confirmations with you guys? Was I like confusing you guys even more by going over them?
It won't hurt.
No, yeah, if you can go over them, like, then yes, please do.
Thank you.
Yeah, no problem. I'm gonna look up like chair confirmation simplified. Simplified chair confirmation. Yeah, I don't see anything like how I was trying to make that chart for you guys. But just like, I feel like practice makes perfect, you guys, with those chair confirmations. I don't want to like confuse you guys even more, but like for sure go over chair confirmations to know the difference between cis and trans. So yes, that is my advice. If you guys want to go over this like a couple more times, that would be like pretty good. Go over those questions in the PowerPoint. Go over book questions if you guys still have time. I feel like doing questions in the book is always really helpful. And if you guys have even more time, like even like watching the lectures, which like isn't like always the most helpful if you guys are like really confused on something. But if you guys have any other questions, feel free to message me in the group me. I'm gonna go ahead and stop the recording.
If you